So I'd like to give some credit to my co-authors here first. The fundament of what I'm going to present here was actually led by Erik Engvall. He was a student in Uppsala, together with Anders Eriksson and Mats André. And I'll also worked together with Kun Lee. He's a student of mine at the Max Planck Institute. So my motivation for going into ion outflow was partly this paper, this seminal paper from '87, almost 3 decades ago, where the role of ion outflow as a supply of plasma to the magnetosphere was discussed. And I've highlighted a little sentence here because there's an invisible component of cold, less than 10 eV, which has never been observed. Now, with the cluster result, these are Mats André's words. This is his GRL paper. It has now been a sort of changed status from invisible to previously hidden. So now we can actually, we can sort of measure this population now. So, outline of my talk, I will just briefly introduce why do ions escape? Why don't they stick on Earth? And then discuss some challenges about the cold ions. And of course, the key thing here is spacecraft charging. And just briefly touch on these new techniques. I will not discuss any technicalities here because we don't have time. Then to some of the results in terms of the source of these cold ions, the fate, and how they react to various geomagnetic activity. And also, at the end, perhaps line out some open issues. So why do ions escape from Earth? Well, it's a simple force balance. There's one force pulling them down and one force working upward. And if you like, you can cast this into a sort of energy balance problem. And this is how you end up with this escape energy, which is, for protons, like 0.7 eV. If they have higher energies, they have the potential to escape. This is a very low energy, and this is sort of the key here. Forces involved, I mean, it can be electric field, of course gravity is involved, centrifugal force, mirror forces, you name it, and they all work in different altitude ranges. The sort of main problem with measuring cold ions down in EV range is spacecraft charging. Because if you put a spacecraft up in space, you have sunlight and a big metal-like structure, which is your spacecraft. And sunlight is, of course, photons. It's energy, with a certain energy. And this will cause photoelectron emission. You will kick out electrons from this spacecraft. So this represents a negative current. And the effect is that your spacecraft will attain a potential with respect to the ambient plasma. And this is sort of the problem, unless you can do something to balance this. And I know on Polar, they try to balance it. On Cluster, there is a sort of mechanism to balance this by emitting ions. But you can also utilize this, this feature. Here is an example from Cluster. This is a measurement taken from a paper by Björn Lübeck recently, where you actually see the spacecraft potential with respect to the ambient plasma. And in the lobes, this potential can be very high, in this case up to 60, 70 electron volts. And that is, of course, a problem, because when your cold ions, few electron volts, come up along the field lines, up to the spacecraft, which is now sitting on a high electric potential, they will never reach the spacecraft. So this is the problem we have. So however good your detector here is, plasma detector, your plasma instrument, the ions that you want to measure, they never reach the spacecraft. And something interesting, which also is sort of the key here, is that you get what we call a wake effect. You get a sort of region which is void of protons. But the electrons, far more mobile electrons, they can fill this. And the effect is you get an artificial electric field here, a wake electric field along the flow direction. And this is what Cluster is actually utilizing to measure the flux of these cold ions. So this sort of invisible population is what you don't measure with a particle sensor. And when we use this new method here, we don't really care about the shape or the distribution function at all. And we also don't know anything about the species here, but it is mainly protons. The method is actually less sensible to heavier ions. This is where Cluster comes in. Cluster is a polar orbiting spacecraft configuration, actually 4 spacecraft, 4 by 20 RE orbit, and it traverses, actually spends a lot of time in the polar regions, in the lobe regions, so it's actually very good, well suited to do ion outflow studies. There are 2 instruments measuring the electric field. The one to the right here is the sort of classical dual probe instrument. Essentially 2 long booms, and you measure the potential difference. Can only measure in spin plane, so it's a 2D measurement, sort of 2D measurement. And it has these wake effect problems if you are in a very low density plasma. But it has a high time resolution. It works in all regions, so it's a fantastic instrument. But it's complemented on Cluster by the EDI, the electron drift instrument, which is a sort of solid state thing. It emits an electron beam, and upon return, it actually measures the drift step, which is typically caused by an electric field. Sometimes a gradient in the magnetic field, but there are methods to sort of distinguish between electric fields and gradients here. Good thing about this measures the true convection electric field, nothing more, nothing less. It's very precise. It is insensitive to these wake effects because it sends the beam on a tour around space before it returns. Drawbacks is it's not very good if you come into regions with high background intensity of electrons, or if you have a strong time varying B, and so on. And of course, for those who work with a wave instrument, it creates some havoc to the wave measurements. So what we do, we use EFW, spacecraft charging, to derive the electron density, which is sort of by definition the proton density also, or let me say ion density. Then we use a combination of EDI and EFW, and the wake electric field and the convective electric field to find the outflow velocity of these cold ions. And then we calculate the flux from this. The electron density derived from spacecraft potential is a fairly old technique. With Cluster, it has been refined, better calibrated and so on, and we have more data, etc., etc. But it is essentially an exponential dependency between the electron density and the spacecraft potential. Bulk flow velocity is obtained from this wake formation. So essentially we use a combination of EDI and EFW, and we derived the field-aligned parallel velocity, the red little vector U parallel here. I think I just referred to the papers by Erik Engvall and his PhD thesis for all the nitty-gritty details here. Now to some results here. We have, I will show 5 years of data, but this is actually now extended. So we have about 1 million records a record in this sense is one measurement of an outflow event. So I will start with just showing the outflow rates, the number densities and the velocities. Then I will go and show some results from a paper by Kun Lee, focusing on the source. Where do these come from? Where do the cold ions come from? With some response to geomagnetic activity. And then a few results about the fate of these ions. Where do they eventually end up? Outflow rates. I just picked these from Erik Engvall's PhD thesis. So the average cold electron density is of the order of 0.18, but as you see, the distribution is fairly skewed here. So the sort of typical density, the mode, is much lower. Average velocity, I mean, Andrew mentioned it here, of the order of 20 kilometers per second. Average from this data set, 26 kilometers per second. And if you now do a bit of integration, take the polar cap area and put in these numbers and calculate, you end up with a number which is of the order of 10 to the 26th ions per second. Which means that these cold ions, they actually constitute a significant part of the total outflow. And this is also sort of the key point in Mats André and Chris Cully's paper from last year, or actually from 2012 now. Just for comparison, I just looked at the literature. I don't know how realistic or how updated these numbers are. But the solar wind apparently, I mean, day-side reconnection essentially, contributes of the order 10 to the 24 to 10 to the 27th. Very dynamic, of course, depending on IMF direction. High latitude, this is a paper by Xi et al., fairly recent paper. They mention a number of up to 10 to the 27th. So sort of on the same orders of magnitude as our 10 to the 26 ratio that we have. This is from a paper by Kun Lee. He was a student of me at Max Planck. Then he actually did some particle tracing, all these measurements. So we have the magnetic field, we have the velocities, the guiding center approximation, and we try to trace these ions back to the level here. Quiet, moderate, and disturbed. Well, disturbed is less than -20, so it's not really storm time. The sort of key elements here is you see expansion, contraction of the polar cap, quiet, contracted polar cap, small region of outflow, disturbed, more extended polar cap region, and higher total outflow, as one would perhaps expect. Response to geoactivity is one thing. Perhaps if we look into details here, we can see some extra outflow from the auroral region, top picture, and perhaps we see signatures of the cusp here. So, I mean, recall, this is cold iron still, but there may be some forces that also extract more cold ions here. Thank you. We also did a study on the fate of these ions. Where do they, what happens to the cold plasma? Once again, we used same data set, the outflow and the density. I did some convection study using EDI. So we had, and of course we have a good model of the magnetic field. And we did exactly the same thing. We did a guiding center tracing now from the spacecraft and out to the plasma sheet, the landing region. And once again, I show low geomagnetic activity and sort of disturbed conditions. This is actually called KP sorted in this case. So low activity, transport further tailward and more dispersed. High geomagnetic activity, shorter transport ways. Most of them end up inside 50 RE. And something interesting we find, and we can't really explain, is there is a sort of pre-midnight preference. There's a dawn-dusk asymmetry, which is sort of interesting. So to sort of summarize the fate of the ions, if you have quiet conditions, you have very little convection, which means that whatever comes out is essentially transported downtail and lost. The other way, if you have disturbed conditions, you typically have a strong convection and a fast transport down to the plasma sheet, supply close to the Earth. And of course, everything in between. Altogether, we estimate that 80 to 90% of these cold ions, they are actually just recirculated. Just 10% get lost downtail directly into the solar wind. Of course, there's a secondary issue. What happens when they start drifting around? And this is when you have sort of the plume things, you leak them out on the day side with all the effects. I read some numbers, 2 times 10 to the 26th, which I picked up from a paper by Borowski and Denton. This is storm times though. And of course there are some interesting effects, quenching of reconnection and you name it. I'm quite sure we will come back to this during this meeting. So just to summarize, the sort of key point is the cold ions, they do constitute a significant fraction of the plasma, large regions of the magnetosphere. Outflow rates, 10 to the 26 seconds per second. This is actually a significant loss. I calculated this and come up with like 60,000 tons per year, which is actually quite significant. 10% directly lost. The fate mainly governed by convection. And of course, there are some open issues here. The mass balance. I mean, when you lose 60,000 tons of plasma every year, do the Earth essentially evaporate into space? Well, fortunately, it doesn't, but that's something we would like to look closer into. And then there's this dawn-dusk asymmetry that we also would like to look into. And this is also why I'm here. I'd like to hear from you what you have to say about it. So thank you very much.
Okay, questions for Stein? Yes, Jim. Let's see. Let's get you a mic. Here.
Thank you. For your mass balance, when you discuss the fact that the trajectories, of course, go down to the tail closer to the Earth when convection is stronger, did you take into account that during those intervals, that's exactly when you get the X-line forming closer to the Earth, and you get far more mass loss down the tail in the plasmoids and the post-plasmoid plasma sheet? It's a complication that I think you need to consider.
It's something we actually do consider, but we sort of find as a sort of secondary loss. If it comes down here, I mean, eventually it will be lost either through, as you mentioned, the plasmoid, or perhaps through the front side, through the plume. So yes.
Okay, but 20R, tailward of 20 RE, that plasma goes down the tail.
Right.
Fairly short order.
A comment about oxygen mass loss, which is of course not what you're talking about. Back in DE times, Rick Chappell and his group and Andy Yao and Ed Shelley and I working on the DE1 energetic ion mass spectrometer came up independently with estimates that we would lose all the oxygen in the atmosphere on geological timescales. Our paper, Andy Yao's paper, was rejected by GRL because it was too trivial.
But that's sort of a different. I mean, there are comets, there are micrometeorites, there are dusts. This is also we should consider these kind of things also, not just the plasma.
I actually want to follow on with Bill's question or comment. This issue of losing oxygen and whether that corresponds to water is one of the things that we should look at in this meeting, because I think that's not clear. It tends to be, especially when we look at the other planets, there's all this question, we look at Venus and Mars, why they are dry and the Earth is wet, and it's argued that the loss rates are substantially different. They're not. They're very, very similar. The other point I want to make is if you take the loss rates that you cited, about 10 to 25, 10 to 26, that corresponds to 8 to 80 centimeters of water over the lifetime of the Earth. So there's not a lot. There's a lot of reservoirs of oxygen in this system. So you've got to be very careful about how much you think these outflows in fact constitute.
I'd love to make a comment. A couple of things. In terms of the pre-midnight, the modeling that you showed was focusing on the meridional sort of flow that gets it into the tail. I think the modeling, the trajectory modeling that Dominic Delcourt has done would show a drift toward the pre-midnight as a result of just the three-dimensional movement in the tail. The second point, I think, which relates a lot to where the particles go once they make it into the plasma sheet, is that they're going to get energized there as they drift across in the cross-tail electric field. They're going to get energized, and they're going to start to look like the plasma sheet particles in energy, and then they're going to move like KeV particles rather than EV particles, and as they drift in, they may even become ring current particles, start to look like the lower energy part of the ring current, and then they're going to have a lot more circulation to them and less sort of push out the front. So I wondered what you thought. You may have done some work like that, Steve.
Certainly. Many of the processes that you describe is actually taking place in the plasma sheet. It's plasma sheet processes. And we didn't really consider those. But the landing point maps that I showed, they were actually slightly before the plasma sheet, and they were still sort of cold there. So I think there's also an asymmetry in the transport, actually, and we see that with the convection measurements from EDI, just purely the lobe convection. It's simply asymmetric.
Any other, let's see, back here in the back, Pat, I think. I guess I've got it.
I think the comment about durable loss of oxygen and also hydrogen from the magnetosphere is really interesting. And now that we're bringing in the other planets, I think when you really look at Mars and Venus, where they don't have the magnetic field that allows you to recirculate 80 or 90% of it, then you really do get 10 or 20 times the total loss, and that explains why Venus and Mars are dry today. And I think when people talk about habitable planets, here's an effect that a lot of astronomers really don't take into consideration, that you may need a magnetic field in a planet to retain its water.
Well, I just have a comment with regard to magnetospheric imaging and how it relates to outflow and oxygen recirculation. During the image mission, the HINA instrument, which measured, I think, in the sort of tens of keV per AMU, there was a strong correlation between that sort of higher energy oxygen and substorm activity. And the presumption based on models like what we saw here and Maching-Fox models is that the stuff gets sucked out of the ionosphere, pulled into the plasma sheet, and then re-injected in the substorm. And thus you would see that delay in the oxygen injection. What we're seeing with twins, which sees in a few keV per AMU, is a little bit of a different profile. We're seeing a much more rapid transport of oxygen into the ring current. We're seeing ring current oxygen ramping up with the main phase of the storm rather than being correlated with substorms. So I just thought that was an observation worth throwing into the till.
Of course, the transport times, these are cold ions. I was talking about velocities of the order of 20 kilometers per second. So, but if you have a strong convection, you can certainly have a fairly fast transport down to the inner plasma.
Okay, Stein, thank you very much.